Okay, so on Tuesday we looked at surjective submersions as generalizations of open covers, and I hope to have convinced you then that that's actually a good tool. Not just a concept, but actually a good tool to do technical calculations, and in particular for the torus. So we'll continue on that theme. So today I want to introduce what bundle gerbes are, which are defined with respect to a particular surjective submersion. And then we'll take a step back and I'll give a brief introduction to T-duality, and then tomorrow we'll combine everything. So briefly, so last time we introduced surjective submersions. So these were maps between smooth manifolds, which were surjective as well as surjective on the differential, on the tangent bundle. And we saw a few examples. The main examples were principal bundles, and the other main example was the surjective submersion given by an open cover U. Now I kept saying that everything that I do is basically a generalization of the open cover situation. So most of the sort of calculations or proofs that I did can be found in the literature for open covers. I asked Paolo to put some old lecture notes on the site where I give a brief introduction to check cohomology and related concepts. So that if you're not familiar with check cohomology, which is cohomology with respect to open covers, then you can have a look at those lecture notes, or if you just want to have a brief reminder of the various theorems. I don't know if they're already on the web or not yet. Okay, never mind, they should be soon. So they are? Okay. So you can look over there to see the various concepts in the context of open covers, in the context of check cohomology. It also has some notes on T-duality, etc., which will also be sort of complementary to what I'm doing here. Okay, so most importantly, we were able to define a cohomology theory, which I called submersion cohomology. So that is based on cochains with respect to a submersion y over m, and then with some coefficients, which I'll typically take, well, either z or r or maybe u1. And later I'll take also coefficients which are forms, q forms. But let's say z for the moment. So these are functions from the fibered product with p plus 1 components to f. And I recall the fibered product, well, is a submanifold of the Cartesian product where you fiber over m. So you identify, so you require the points project to the same point in m. Okay, so the differential of this complex has a nice form. So differential, so I need to give it, say f is an element of Cp. I need to give the delta f in Cp plus 1. Okay, so delta maps Cp to Cp plus 1. So I need to evaluate it on p plus 2 elements. So I usually label things starting from 0. And this is just the alternating sum, where you take f and you omit the ith element. So this is evaluated on p plus 1 elements, which is indeed what Cp is. So again, this defines a differential, which I gave to you as an exercise. I hope people work through that exercise. I'm not going to write down the solution. Or maybe you often also see a more condensed notation. So if I have, for instance, y2, it maps to y in two different ways, and y3 maps to y2 in three different ways. And these ways are just omitting the ith variable, so pi 0, pi 1, pi 2. So I can map an element y0, y1 in y2 to y by omitting the first element. So this is y1. So this might be different than notation you're used to. I mean, normally you might be used to pi 0 being the projection on the y0, but if you look at y3, this definition makes more sense, because such a map has to omit one variable, so it's better to indicate it by the variable you omit. So if you do that, then del f is just the sum of I equals 0 to p plus 1 minus 1 to the I of pi I star f. Okay, we had some operations on this cohomology or on the cochains. The important one was the cup product, or actually a series of cup products from Cp cross Cq to Cp plus Q minus I, where the normal cup product or standard cup product is the cup 0. And I concluded with a fundamental relation. So if f an element of Cp, g an element of Cq, then on cochains we have the following relation. So the I minus first, I think I labeled them, yeah. And then this indicates a graded commutativity. Okay, I should be writing a bit bigger, but these notes are also on the web already, so if the cup product, the ith cup product would be graded commutative, then this would be 0, but in general it's not 0. Let me not make a mistake, so read it from the notes. Some factor of plus or minus 1, and then here you have the statement that would be 0 if delta is a derivation. But the violation of delta being a derivation of cup I is precisely the left-hand side, as well as the other way around. So this is true for I bigger equals 0, provided we just set cup minus 1 equals 0. So for I equals 0, left-hand side is 0, the right-hand side tells you that the differential is a derivation of the lowest order cup product. So these cup products are, or the 0 cup product is sort of analogous to the wedge product of differential forms. But of course, in differential forms, you have graded commutativity. So the right-hand side is always 0. So the higher order products don't exist for the wedge product. So this is a more complicated structure. But what you see, for instance, is that del 0 is graded commutative on cohomology. So not on cochains, but on cohomology classes f and g, the delta f and the delta g is 0, and then the graded commutativity is just a co-boundary. So in cohomology, that's 0. So on cohomology, you have a lot of nice graded commutative structures, but not on the cochains themselves, and that complicates things a little bit. So my main example of where this is useful, as I said, is a torus. So the example that I already had, so this is, let me first do the circle. So where y maps to e in the power 2 pi iy, where I think of S1 as the unit circle in the complex plane. Now I claim that the submersion cohomology, and I'm not going to prove that today, but I might prove it tomorrow, or at least I'll give you a hint of the proof tomorrow. In principle, you could compute it by using the theorems which relate such a cohomology to check cohomology and go through the zigzagging which I mentioned yesterday, but I didn't state the precise theorem, so but anyway, so what I claim is that this is isomorphic to the check cohomology of S1. So you can actually find representatives of check cohomology, which are typically difficult because you have to find an open cover of S1, or for higher tori it's more difficult. And this, of course, you very well know as Z in degree 0, Z in degree 1, and 0 in degree bigger than 1. So again, if I would write down representatives in this check cohomology by choosing an open cover, it looks ugly. I have to assign integers to all elements of the open cover, making sure that everything patches on overlaps. And then if I want to take wedge products of it, it just becomes a mess. It becomes very hard to do calculations with, and even more so for higher ranked tori. But with this statement, yeah. Sorry? Yeah, universal covering maps are in general surjective submersions. It works for every surjective submersion. Oh, this is isomorphism. Definitely not, no. So I gave an example yesterday. If I have a surjective submersion for which there exists a global section, then this, what I defined as the submersion cohomology, is 0. So you need, yeah. In fact, I don't know any other example than tori where this is an isomorphism. In general, if you take a principal bundle, well, this I'll come to tomorrow, but if you take a principal bundle and compute a principal G bundle and compute its submersion cohomology, you'll find it's just a group cohomology of G, which is not equal to the cohomology of P, but C's part of it. Okay, but I'm running ahead. But yeah, okay, so I just want to write down explicit representatives. And again, I'm presenting this as a technical tool to really work with classes on the torus, or torus bundles, in fact, and to do things like T-duality explicitly on representatives. Okay, so H0 is just a constant map. H1, I'll claim, so recall, I'm using a similar notation as in the Ram cohomology. So in the Ram cohomology, the H1 of S1, R or the Ram, whatever, well, equals R, and it's generated by something which is usually denoted as d theta, or maybe if I denote the angle as x, as dx. So this is, yeah, sort of a hand-waving notation because it's not the d of something that lives on the circle. So this is not an exact form, but it is a closed form. So in the case of surjective submersions, of this particular surjective submersion, I'll introduce, say, a one cochain delta y. So I have to tell you how it acts on y0 and y1, and I just take y1 minus y0. So obviously that's a good cochain because it maps to the integers if y0 and y1 are in the fiber product. So it's integer valued, and you can easily check that the delta of del y, so let me do explicitly y1, y2. So first omit the y0, so I get y2 minus y1 minus y2 minus y0 plus y1 minus y0. And if I did everything correct, it should come out as 0. So it's indeed a cocycle. It's not exact because it looks like it's the del of the function y, but y is not a function on the circle. So y is not an integer in general. Sorry, y is not an integer. Y lives in R. So it's not an exact thing in my submersion cohomology. Okay, so I claim del y is the generator of H1 of this cohomology. And now I did something stupid. I erased my formula for cup products. Well, so as I said, and the differential is acts as a derivation on the cup product. So this is also a closed form. So it would be a non-trivial element of H2 unless this is a coboundary. So with my formulas for the cup product, you can see that 2 of this is minus the del of del y, cup 1 del y. Okay, I don't know, maybe I should write down my formula again. F cup, so F I minus 1g plus sine F cup I minus 1g equals minus to some power del F cup I g plus minus del F cup I g minus the sine. Hope you have it all in your notes now. Okay, so for del y, the del y and the del y are 0, so you only have this particular term, so that's the formula. Well, maybe it's useful to just show why this is true. So del y, cup product. So that's a one class with a one class, it's a two class. So this is, I've given you the formula for the cup product, so this is just del y, y0, y1, and the cup product is just repeating the last and the first index of the next one, which is the same formula as you have for Czech cocycles. So this is just y1 minus y0 times y2 minus y0, y1, sorry. And I've also given you a formula for the cup 1 product, and I've told you that's just y1 minus y0 squared. Well, in general, it's the f of, okay, it's just choosing two elements equal, so it's y0 minus y1 squared. Okay, so it's a bit trivial, but it's good maybe to just do an example which you can all work through. So if I do the del of y0 minus y1 squared, so the del of del y cup del y in y0, y1, y2, I just get y1 minus y2 squared minus y0 minus y2 squared plus y0 minus y1 squared. And well, you can work this out. This is minus 2 times del y cup del y. It's minus 2 times the guy over here. Okay, now you should be a bit worried because it looks like del y cup del y is a coboundary, but I'm working over the integers. So really I'm not supposed to divide by 2. So it seems almost like I conclude that H2 of the submersion cohomology is isomorphic to Z2. If I take twice the generator here, I get 0, but yeah, I'm not allowed to divide by 2, so what's the what's going on here? And it actually took me quite a while to figure it out. I mean, the solution is straightforward, but this is the right formula. I can just add a del y. That's also closed so that you don't see this in this formula. But here I have, so this is an integer n, so this is something like n squared. And I just add n, so this is n times n plus 1, which is something I can divide by 2. So, so indeed del y, cup del y is a coboundary operator, is a coboundary. So, but you see, if you work with explicit representatives of these cohomology theories, you have to worry about the cup product not being graded commutative. You get all these extra terms, but in principle you can, it's straightforward to handle them. Okay, my earpiece is playing up a bit. So more generally, if I have an example which I want to do is the 3 torus. So then I just take the 3 copies of my surjective submersion. So then I can construct representatives of the cohomology of the 3 torus in terms of this surjection, in terms of this submersion cohomology. So for degree 1, I have delta x, del y, del z. If x and y and z are the coordinates on R3. Yeah, for the degree 2, I have, of course, all the other ones, etc. So very easy to construct representatives. And in fact, it's not that hard to construct representatives of, not over the torus, for the torus, but for general Fornil manifolds. So torus bundles over tori. Okay, so this is a very, again, I see this as particularly as a technique. It works very well for the torus. I haven't really explored it for many other surjective submersions of other manifolds. But in particular, if you want to study like T-duality or mirror symmetry, you typically work with tori. And if you want to study orbifolds, you typically work with tori. I said one of the motivations I had for doing this, for developing these techniques, was to do things to look at T-duality or mirror symmetry for global toroidal orbifolds. And in that case, if you work with open sets, your finite group action often takes you out of the open set. And you have to really do something very construed to let your group action be compatible with your open set, open cover that you choose. But here, with surjective submersions, it's often very easy to lift the group action to R3. So it's much easier to study global toroidal orbifolds using these surjective submersions than open covers. Okay, so now I want to go into bundle gerbes.
Whether these cup products,
yeah.
They make it an algebra, so you have, is an associative algebra.
So,
stick to a specific one. You
are. Yeah, so the cup products are associative, the zero cup product, not the higher ones.
No, the higher ones.
The higher ones are not associative. So this algebra of these cup products can be mapped into an A-infinity algebra by some generic nonsense. I mean, the actual map is not that easy to come by, but you can do it for low order. But I don't think there's explicit formulas for how to do this, but it should be possible.
So you
So, yeah.
Has a derivation in a infinity bimodule?
Yeah. They're also related to messy products and things like steam-dot squares. And they're all, yeah, part of a complete algebraic structure.
Just a very naive question. Is there any sort of equivalent on the rank cohomology again with the wedge product or something?
An equivalence, well,
some sort of, I don't know, isomorphic structure.
well, you can always map this to the de Rham cohomology. That's over R. So I mean, you lose all that structure of these extra terms. But I'm not sure what you have in mind. But
No, I was just wondering if there were some sort of higher products on differential forms, for example.
oh no, you don't have the higher coproducts, no, because you have graded associative, graded commutativity on the wedge product. Yeah, if you write down the differential algebra of forms as an A infinity, it just cuts off at the first term. You don't have the higher terms. Okay. Okay, so a brief introduction to bundle gerbes. So bundle gerbes are associated to my submersion cohomology. So in particular, I want to just restrict myself to U1 bundle P gerbes. So U1 is my coefficient ring of my cohomology then. And they're given by, well, they're classified by HP plus 1 of, well, general M U1. So the check cohomology like this. So in particular, -1, well, U1 -1 bundle gerbes, bundle P gerbes. Should be associated with H0. So H0 we have already seen. H0 are, for a given submersion, are given by cocycles which satisfy this identity. This is the cocycle identity. I'm writing U1 multiplicative. This is the cocycle identity for 0 cochains. So we've seen that these correspond exactly to functions on M. That was my motivating example. So more interesting are the case of bundle 0 gerbes. Okay. So what's interesting for string theory are the bundle 1 gerbes, where the so-called B field enters. So these are, well, these are usually just called gerbes. But there exists actually a lower dimensional or lower analog, the bundle 0 gerbes, and it turns out that these have to do something with line bundles. So a lot of the things which I'll be doing here, I can also do for bundle 1 gerbes, but I don't want to get too technical, so that's why I'm presenting this case and not the other case in so much detail. So for me, a bundle 0 gerb is a collection GYM, a triple GYM, where where I have a surjective submersion. And of course, this G is an element of C2. It's a 2 cochain, or 2 cocycle in fact. So satisfying del G is 0. So it satisfies so this is G Y1, Y2. And right now I'm considering U1, so I write it multiplicatively. Y0, Y2 minus 1, G, Y0, Y1. This should be 1. Or maybe I should draw it in a picture. So I have my surjective submersion. Then I have the fiber product. And I have this map G to U1. Okay. There's a few things you can see from here. If I take all the points equal, so this is for, in Y3. If all the points are equal, then you see that GYY equals 1. And furthermore, if you take Y2 to be Y0, you see that Y0, Y1 is just Y1, Y0 inverse. Okay. Yeah, sorry. Yeah, just keep reminding me because I will go slower again, smaller again. So. Okay, so I claim these have to do something with line bundles. Why I wrote U1 there? Yeah, that's the identity in U1. GYY equals 1. If I take all the elements equal, then I have G times G minus 1 times G equals 1. So these two cancel, G equals 1. And normally you would take this such a relation as a normalization maybe of your cochains, but in this case it follows from the co-cycle condition. Well, I haven't, yes, it will be related to the co-cycle description of a principal bundle, which is what I'm going to show you now. Okay, so to relate it to principal bundles, you have to somehow put a different equivalence relation, not isomorphism, but something more general, because these constructions depend on the surjective submersion. So you want to sort of encode that in your equivalence relation. So, I have to tell you, for instance, what a trivial zero Gerb is. So a trivial zero Gerb is a triple, which is a co-cycle, where G is a co-boundary, Ym. So here the G needs to be the del of H, which is H Y1, Y0 minus 1. Okay, we also have a dual. The dual is just the inverse with the same surjective submersion. The inverse satisfies the same co-cycle condition. And we have a multiplication, which will make the set of zero Gerbes into a group. Multiplication is just, if you have two of those, maybe with different co-cycles, different surjective submersions, you just take the product of the two co-cycles, you take the surjective submersion, which is the fiber product of Y and Y tilde. That gives you a multiplication. Okay, I also need to talk about morphisms. And I'm already writing smaller, I guess. So please keep reminding me. It's a bad habit of mine. I need to talk about morphisms of bundle zero Gerbes. Let me So a morphism of a bundle zero gerbe is in particular a morphism of surjective submersions. So we knew what that was, that I introduced 2 days ago. So that's something which makes the following diagram commutative. So again, these are all, I work always with smooth manifold, smooth maps, etc. I'm not going to mention that every time. But rather than being just morphisms of surjective submersions, they should also, of course, do something with the co-cycle. So here's my picture. So I have these fiber products, and I have maps to U1 from the fiber products, which are G tilde and G. And using phi, I can construct a map over here, just by applying phi to each element of the fiber product. So phi 2 on, well, y0, y1 tilde is phi y0 tilde phi y1 tilde. So the relations I want are that pi tilde equals pi after phi. I want g tilde equals g after phi 2. So this is a morphism of bundle zero gerbes. So once I have morphisms, I can talk about isomorphisms, of course. But an isomorphism will be, particular isomorphism between the two surjective submersions, while if I want to, say, think of things more inherently related to the base manifold, I should allow for all possible surjective submersions. So the good notion of when two bundle zero gerbes are equivalent is something called stable isomorphism. Well, so two bundle zero gerbes are stably isomorphic so let me call them G, Y, M, G tilde, Y tilde, M. If and only if there exists a trivial bundle gerbe such that they are equal up to this trivial bundle gerbe. Well, isomorphic up to this trivial bundle gerbe. So this will allow you to change the surjective submersion. I can also formulate it by bringing this to the left-hand side by using the dual. Okay, now I want to talk about the relation to U1 principal bundles. Does everybody know what a principal bundle is? Can I see hands who doesn't know? Oh, okay, good. Then I won't repeat that. Yeah.
If you take M to be a point, so Y to a point,
Yeah.
and then the map, this co-cycle that you built,
Yeah.
I just think of this as a map from M to BG. From Y to BT.
For a principal bundle? Yeah.
No, I meant if you take M to be a point, Y to the point, Y mapping to the point, and
Yeah.
the co-cycle you have, is it the same thing as a Y to BT?
If G is a group, you mean? Yeah, I think that's exactly the same. Yeah.
last time you talked you talked about locally trivial vibrations. For you, is it the same as a fiber bundle, or do you make a distinction?
Well, a principal fiber bundle has a G action. A locally trivial vibration doesn't have to have a group action.
Yeah, but putting apart principal bundles, do you make a distinction between fiber bundle and locally trivial vibrations, or not?
Well, a fiber bundle doesn't have to be locally trivial, but locally trivial fiber bundle, I think that's the same as a locally trivial vibration.
Okay.
Yeah, is that right?
Yeah, sure.
Unless I'm mistaken here, I don't know whether Ron wants to correct me on that or. Okay. Okay, so I won't need to tell you what a principal G bundle is, but just yeah, the theorem here. Well, so I already said that bundle zero gerbes form a group where the trivial element is the trivial bundle gerb, the identity element. The proposition or theorem is that the group of stable isomorphism classes of bundle zero gerbes is isomorphic to the group of isomorphism classes of principal U1 bundles. Okay, so maybe you know that principal U1 bundles are classified by H1 of M with coefficients in the sheaf of U1 valued functions. So in particular, I have to associate an element in here to any bundle zero gerb, and that we've seen already how to do that. We just take an open cover. In fact, we take a good open cover of M in such a way that we have a morphism of surjective submersions. One of my theorems from 2 days ago was that this always exists. Now, a good open cover, if you take the check cohomology, it computes this particular check cohomology. So the induced map on the cohomologies, well, U1, will just compute me my check co-cycle. Right, if you want to have it explicitly, the check co-cycle corresponding to a principal bundle, so which gives you the, if you want, the transition function on overlaps, is just given by my G of my bundle zero gerb for a set of sections of my open cover. Right, so okay, so I don't want to prove every little detail of this theorem. I'm already seeing that I won't get anywhere today, or anywhere near I wanted to get to. But yeah, essentially, I'll give you the construction. So I'll have to construct out of every bundle zero gerb, I'll construct a principal bundle, principal U1 bundle, and that construction is as follows. I just take the product of Y with U1 and I divide it by an equivalence relation. And the equivalence relation is that Y0, Z0, so Z is an element of U1, is equivalent to Y1, Z1 if Z1 equals Z0, GY0, Y1. So if they're related by by my cocycle. Now, of course, if you're familiar with principal bundles, if you do this for the submersion given by open cover, this is precisely the construction of a principal U1 bundle out of your check cocycle. So there's nothing new here. And the other way around, if I have a principal U1 bundle, I can construct a bundle 0 gerb by just taking, so a principal U1 bundle, so I have to construct this G, but P to M was a surjective submersion. So G, well, if I have a principal bundle, then if I take an element in the fibered product of P with itself, that's precisely taking two elements in P which map to the same base point. But the action of U1 is free and transitive on the fibers. So P0 and P1 are always related by, uniquely related by a group element. And I call that G group element GP0 P1. That satisfies the cocycle condition. And that's the cocycle I need in that definition to make it a bundle 0 gerb. Okay. Well, so now you need to show that these maps are, well defined on equivalence classes, etc., etc. So I was going to do part of it, but I think I might skip that and just have a little break and then continue afterwards. I'll put a reference to where you can find it, some all details in my notes. So that you may consider an exercise to study those notes. Okay, so before I go to bundle 1 gerbs, which is the case I'm mostly interested in because it has to do with the B field in string theory, I just want to tell you what a connection on a bundle 0 gerb is. So a bundle 0 gerb, G, Y, M, a connection A is an element, is a one form on Y, satisfying that if you take the submersion differential, that this is equal to G minus 1 dG. So G is a U1 element, or maybe I should say D log G. Or maybe written out in full, something, so this needs to be satisfied on Y2. So this is by definition the one form in the point Y1 minus the one form in the point Y0. This should be equal to, well, D log G Y0 Y1. So this is not particularly difficult to guess, because if you have an open cover, then this is precisely the condition that that the gauge field on the base should satisfy on overlaps. Right? But you can just write down the same thing for connections on bundle 0 gerbs. Okay, well, if this is the case, then the D of A, so that's a 2 form on Y. Well, the D and the delta commute. So this is the D of the D log, so this is 0. So this implies that the D of A in Y1 is the D of A in Y0. So that means that the D of A is something which is globally defined on M. Right? So the D of A is something which is actually a 2 form on M, which of course we identify with the curvature. So the curvature is closed. So having a connection on a bundle 0 Gerbes gives you an element, well, gives you an element F or a class in H2M. Okay, these are things over R, a form with values in R. So it gives you the RAM representative, if you want, of the class of your bundle 0 Gerb. So it's good to write down a picture. So I have two differentials, d and delta. So F is, well, in my labeling of my cochains, it's really a degree -1 cochain in the delta direction. And then it's a 2 form here, 1 form here. Here's A and here is G. And they satisfy this zigzag condition that if you take the d of log G, and I should probably say I push all factors of 2 pi I under the carpet. Sorry.
Yeah, so F is a 2 form, it's a closed 2 form of integral period.
It's a closed 2 form, yeah?
With integral period.
No, this is a connection 1 form with values in R. Well, with integral periods, yes, but it's an R valued, just a form.
Yeah, but when you integrate it on the closed loop,
Yes, that gives integer values, yeah. So the d log is the del of this one, and the d of this one is the pullback of F to the submersion manifold. So you get these nice zigzag things, which you also get in the context of check the RAM cohomology. So so I don't want to go into differential cohomologies, but really this pair gives you an element in a different cohomology theory called differential cohomology. So the lecture notes that are on the web give you also a little introduction in differential cohomology, but basically I want you to just remember that these connective structures are related by a double complex. And if you want to do this more generally for higher P, you'll need to solve such things. So you need to, basically it's not hard to see that if I take the D here, that this is the del of something, or is the pullback, the del in this case, the pullback of some F defined on the manifold. But if you want to do this for somewhere else in the complex, then you need a theorem. And the theorem is the following. It's essentially that for any surjective submersion that the columns are exact. So let me write that down. So I'm looking at Q forms with values on the P+1 fibered product, or in other words, I'm looking at P cochains with values in omega Q in a ring of differential forms. And then the theorem. So this is a very useful theorem for any surjective submersion. This sequence is exact. So if you just take the del going from omega Q to omega Y, so I've done the Q plus 1 example there. Is exact. For all cubic and Z. Okay, I have a proof in my notes. The original proof is attributed to Michael Murray, but I believe that's not completely correct, that proof, because he gives a proof for locally trivial vibrations, which I don't think carries over to surjective submersions. But you can basically copy the proof in Bot and 2, who do this for open covers. So maybe I'm not going to write out the details again, but the proof is based on the construction of a homotopy operator. So again, you have this omega q yp, so this sequence, del, del, etc. So I construct a homotopy in quite a similar way as I've done before in one of my other proofs, but in this case this homotopy operator satisfies the following relation. So indeed, if you apply this to a if you apply this to a co-cycle, so co-cycle such that this holds, then you find, if you apply that relation, that this is a co-boundary, so which means that the sequence is exact. So let's see. So in the notes I give an explicit formula for this homotopy operator K, and then you can just check this relation just by hand. So again, the exercise is just read that proof in the notes. Now I really want to get to bundle, well, to T-duality, otherwise I'm not getting to the punchline tomorrow. Tomorrow is mostly new stuff. But I haven't introduced bundle 1 Gerbes. So I'm going to do that, I think, very, very quickly. But yeah, basically everything is set up in the same way as for bundle 0 Gerbes. You need to define a stable isomorphism, etc. So bundle 1 Gerbes are related to elements of H2, or H2 of M with U1 valued coefficients, or otherwise H3 of M Z. And let me just draw a picture what they are. So you have a surjective submersion, you have this fiber product, and instead of functions you now have bundles, U1 bundles over Y2. So this is a U1 bundle over Y2. Principal bundle. So if Y is just, again, the submersion corresponding to an open cover, it means you have U1 bundles and overlaps. So that's the Hitchin approach to Gerbes, but that generalizes to arbitrary submersions. So now I need to tell you what, well, so this is not all the ingredients. You need to have some product structure on P. I'm not going to spell it out. You need to have some product structure, you need to have some good notion of morphisms and then of stable isomorphisms. But again, what you find out is that the stable isomorphism classes of such constructions are classified by this cohomology. I just want to draw the diagram for a connection or connective structure on such a bundle 1 Gerbe. So it's the same picture, but now in degree higher. So connective structure should of course be a connection on this U1 bundle. So that's an element which is a 1 cocycle here, so that's some element, say, call it C. And it's given by a similar Let's go on a similar condition, how it behaves on triple overlaps now. So the transition function is now h, and then using this theorem you can see that I can now construct something which is a 2 form, B, and is also a zero zero submersion cocycle, and the element here is usually called H. So starting with a connection on this bundle P, you can construct something B, which is called a curving, or I've called it B because in physics you see that denoted as a B field. It's a 2 form. It's a, well, for open sets, it's a locally defined 2 form, and those are the things which couple to strings. Right? Connections couple to point particles. If you go 1 degree higher in form language, they couple to strings. So this is called the B field in string theory. Okay, so that B field is going to play a role in T-duality. It's one of the backgrounds to which the string couples, other than the metric and maybe a dilaton and, well, whatever other massless fields are in the string theory. Okay, so that's sort of the application. Here you see that, yeah, this whole structure of bundle gerbes naturally incorporate fields that you see in string theory. But again, I've set it up in such a way that I don't need to do it in terms of open covers. It works more generally in terms of submersions, which will be in particular very useful in the case of my torus examples. Okay. So now I have about half an hour to give you a little introduction to T-duality. So there's various aspects to T-duality. So T-duality is a transformation between, if you want, 2 different string theories. In this context, it will be a transformation on, essentially, a transformation that relates pairs of a bundle 0 gerb and a bundle 1 gerb to another such pair. So that's on the fields, this is going to manifest itself in some dualizing of this zigzagging as well as the zigzagging for a bundle 0 gerb, and they get mixed up. But it's important for string theory because it's T-duality is supposed to be an exact symmetry of string theory. So it relates string theories maybe on different manifolds and in such a way that you can't really tell the difference. You can't do any experiments which distinguish 2 theories. But there's also a topological aspect to it. So tomorrow I will talk about the transformation of this whole connective structure. Today I'll just talk about the top class here, which essentially classifies the topology of the bundle gerb. And similarly for the other case where I have F, A, and G. So today I will tell you how T-duality acts on these top forms here in this classification, if I have time. Okay, so who has heard about T-duality already? Show of hands? Not that many people. Okay, so I'm just going to, sort of give an intuitive introduction what T-duality is supposed to be. I just want to argue that it is some geometric form of Fourier transform. Look, I really don't know whether I can get very far in half an hour, but so I'll just recall what Fourier transform is. And I'm really taking a step back now. I won't be talking about surjective submersions for a while. Now, Fourier transform, if I have a function, say, on the circle, then I can do a discrete Fourier transform. You've all seen these formulas, maybe you've seen it with different factors of 2 pi, but maybe my factors are not completely correct. But so you can construct a Fourier transform, which is a function of z to r. And of course there exists an inverse. And the inverse is just, this is a discrete thing, something like this. Now, these things generalize. In particular, you don't have to take periodic functions or functions on a circle. You can also take functions on, say, the real line. In which case, so f is a function on the real line. Then the Fourier transform, I guess you want to denote it by p. Well, and the inverse. Something like this. And this can be generalized to, well, in particular, just locally compact abelian groups. And in that case, well, in all cases, if f is a function on a locally abelian group, such as R or Z, then f hat is a function on what is called the Pontryagin dual group. Okay, so this is something very general. But what I want to observe is that there's something strange going on here. In all these formulas, you sort of start with a function, here a function of x, and then somehow you pull out of a hat, you pull a different variable, p, and then you think of the integrand as a function of x and p, and then you integrate away the x. So where does the p come from? I mean, so if you want to geometrize this, so also this thing you multiply with, for each p, this is a character of G. So it's not any kind of function you multiply with. It's actually a character of the group G. And well, the inverse sort of tells you that all functions are spanned by the set of characters. So it's some kind of universal object. And the way to think about it is, so you have your functions on G, and you have your functions on the Pontryagin dual. And you construct something which is called a correspondence. And then the Fourier transform is something like this. You take your function here, so a function from G to R. You pull it back to this correspondence space. Then you multiply it by some character. For each P, this is a character of G, and for each X, this is a character of G hat. And then you push it forward to G hat. In this case, the push forward is just integration. So what's really happening is that you're identifying spaces which are just functions of X, spaces which are just functions of P, but you compare them through this intermediate space, correspondence space. And these kind of considerations actually generalize to geometric situations. So not just functions, but you can do this for forms or sheaves or Yeah, well, you can derive categories, or you can make it as, I mean, any kind of sort of geometric object you can try to construct these correspondences for. In this case, the push forward is just integrating over G. Yeah, so a particular generalization is the Fourier-Mukai transform, where you do this on bundles. Now, actually, the push forward doesn't exist on bundles, but exists on K-theory. K-theory classes, equivalence classes of pairs of bundles. So, yeah, you have to make sure that this push forward exists. That's part of the construction. So to illustrate how this works in terms of forms, and that it's really, yeah, really the same thing, and really the sort of same sort of formula that you get out. I'm going to look at a manifold, M cross S1, so there's the product manifold. So we know the cohomology of this cohomology ring is just by the Kuhn theorem is isomorphic to the cohomology ring of M and S1. Or in fact, if you put in degrees, it's Hn of P is isomorphic to Hn of M, yeah, plus Hn minus 1 of M. And that's because this cohomology is sitting only in degree 0 or 1. And in fact, you have a similar decomposition on the level of forms, well, on the level of invariant forms. So invariant under the action of S1. And M plus N minus 1 M. And of course, the correspondence is just that forms over here are like this, and forms over here, if you wedge them by the generator of H1, you get a form over there. Right, so invariant forms on this product here are of two types, are either a basic form on M or a form on M wedge d theta. So now I'm going to write down what T-duality is in this context. So T-duality in this context is just interchanging these two. So it's a very simple thing. So it's just interchanging this in any form over here, just interchanging the N form with the N minus 1 form. Okay, so if, of course, if I interchange N forms with N minus 1 forms, I don't preserve the degree, but I preserve the degree mod 2. So I get a map from the mod 2 cohomology of P to I plus 1 of P. And explicitly, so P hat. So P hat is the dual manifold, which is just say a dual circle. So I map omega to, as I said, I map omega to something of the form d hat wedge omega, and I map d hat wedge omega to, I've interchanged the order of d theta and omega, doesn't matter. So there might be some minor sign mistakes here. And you basically interchange these two different forms of N forms, invariant N forms on the manifold. And if I've done everything correctly with my signs, so if I have an omega, so an omega which is a combination of this and this, I can encapsulate those two formulas in one formula. 1 plus d theta wedge d theta hat omega. So you integrate away the S1, so in this term omega I need to take this term, so I get essentially this, and for this one this term gives 0, so I integrate this one, so I get that one up to some sign, but I hope I did it correctly. Okay, so you can of course write this as e in the power d theta wedge d theta hat of omega, or as 1 e in the power f omega, where f is this particular 2 form. So again, what I've done here now is I have m cross s1, and I have m cross s1 hat. I have a form here which I'm transforming to a form over here, and I do this through this correspondence space. And the formula is just, well, the formula is, if I call this P hat, then the formula is exactly the same as I had before. So I pull back the form over here. I think I've interchanged my, okay. I pull back the form over here, so omega. I multiply it by, well, I take the wedge product with this particular class, this particular expression, e in the power 2 form, but it only has an expansion for the circle, just in terms of the first 2 components. And then I push it forward by integrating along the original fiber. So this is exactly the same formula, but now I have as Fourier transform. But now for forms. And again, this object is actually quite universal. So f is the curvature of what is called the Poincaré bundle, Poincaré line bundle over S1 cross S1. So there's a canonical bundle. It's the generator of the second cohomology of this space, and it has a curvature given by this expression. So again, this is quite a universal formula, and it immediately suggests that rather than doing it for forms, if this is the curvature of a bundle, you should maybe be able to do something analogous for the bundles themselves, and that is called Fourier-Mukai transform. Okay, so this is the simplest sort of form of T-duality, and I hope it's sort of clear that this is very much related to Fourier transform. Okay, now some physics. What is T-duality in physics? So as I said already, T-duality is a symmetry of string theory. So very sketchy. So let's take a closed string. On, say, M cross S1. So that's in particular described by a map from the string worldsheet to M cross S1. M cross S1 is my space-time. This is my worldsheet. So the worldsheet is parameterized, say, by sigma and tau. Now you want to do the quantization of this string. Okay, so this manifold can contain more information, like a metric or symplectic form, or it can be Kähler or whatever. So there can be more structure, but the structure for a closed string is always this map which embeds the worldsheet into this manifold. Now, if you try to quantize this theory, you find two things. You find momentum modes. So you can't in general quantize exactly on any manifold M, but you can quantize in the circle direction. So the X component in the circle direction, you have momentum modes which are quantized. That's just the Bohr quantization rule, just saying that your wave function should fit into the S1. So the momenta is quantized in the circle direction, and that you have for point particles as well, but for strings you have winding modes. So you have winding modes are when you go once around the sigma direction, that you can wind m times around this circle. And I'm not worrying about factors of 2 pi. It's just so if you wind once around the circle, so you compare the x coordinate. So x is really a coordinate here on r. So in r, it's identified modulo number of times around the circle. So that gives you another integer. That's called the winding mode. And that, of course, you don't have for point particles. Now, if you look at the energy spectrum of such a string, you find that, well, it has contributions from these momentum modes, which are basically, well, just kinetic terms, 1/2 p squared. So these go like 1 over r squared. And then you have contributions from the winding modes. So they come with an energy m times r squared. So my circle has a radius r, sorry. And then you have, well, oscillation modes. And you have all these modes coming from the manifold M. But in any case, they are R independent. So what you see here is that the spectrum has a symmetry. R goes to 1 over R. When you simultaneously interchange your momentum and your winding quantum number. And this is called T-duality. So this is a symmetry of the spectrum, but you can show that it's a symmetry actually of all the amplitudes as well, all the correlation functions or scattering amplitudes. So it's a symmetry of the full string theory. So with string theory, you can't distinguish a circle of radius r and a circle of radius 1 over r. Now, topologically, they are, of course, the same, at least if r is not 0. So this is just sort of the topological part of it. But yeah, it's sort of interesting. So this is, yeah. Whatever you want. Okay, so I think the original name comes from torus duality. People also say it comes from target space duality, as opposed to other kind of dualities. If you do C-star algebras, this is Takai duality. Fortunately, Takai started also with a T. It's actually, Takai duality actually probably predates this string theory type duality. Yeah, so, but either of these two, I would say.
So when you talk about spectrum, you talk about the spectrum with respect to the Fourier thing?
I'm talking about the spectrum of this closed string on this manifold once I quantize it.
Sorry, that's probably stupid. I don't know what that means.
Eigenvalues of the Hamiltonian.
Sorry?
Eigenvalues of the Hamiltonian.
Oh, okay. So again, what is the Hamiltonian?
Oh, I don't want to write it down. Yeah, there's an action principle, and you can canonically quantize this, and it gives you a Hamiltonian.
The spectrum in the sense of Fourier transform.
No, that's.
Okay.
Okay, so this is more complicated if I add some supersymmetry. In that case, it might be a symmetry between different string theories, etc., etc. But this is sort of the basic idea. Now, but this is for a trivial circle, M cross S1, but it turns out you can, I mean, these dualities really act locally, so you should be able to generalize it to principal circle bundles. Principal S1 bundles where it's locally M cross S1, but not globally. And you can generalize it a bit further by adding some background to the string. So you can couple the string to a B field, which is locally defined, as we have seen in the last hour. The thing that's globally defined is what is called the H flux. So this is globally defined. So it turns out you can generalize that picture to a situation where you have a principal S1 bundle or U1 bundle. So that's characterized by some 2 class on M and a H flux or a B field, the curvature corresponding to a B field, which is also an integral class, but that's a class on P. The string lives on P, on M cross S1. So let me write down, and probably finish with that for today, what T-duality does on this particular setup. So it turns out that T-dual of such a situation, and maybe I'll say a little bit of how you would derive that tomorrow, is another S1 bundle, principal S1 bundle. I mean, this works nicely in the case of circles. For tori, it's more complicated. For tori, the dual is not always a principal torus bundle. And you can give the dual data very explicitly. So the dual F is the push forward of H. So if you push forward H by integrating it over the fiber, you get a 2 form. That 2 form is the curvature of the dual bundle, dual S1 bundle. And this is symmetric in the sense that the original one is given by the push forward in the dual bundle of the dual flux. Now, this of course doesn't determine H hat, but H hat is determined by essentially by saying that H and H hat should not change, the components on M shouldn't change. But of course that's not an invariant statement because H and H hat don't live on M. But you can again do this through a correspondence. So H lives here, H hat lives here. It turns out that H hat is uniquely determined by requiring that if you pull them back to the correspondence space, then they give the same class on this correspondence space. But just an example. And again, this is just topological. I'm talking about isomorphism classes of principal U1 bundles, etc. If I want to talk about the differential forms on these spaces, I go to these whole Deligne classes, which I've introduced and which I'll come back to tomorrow. But let's say if we work with circle bundles over S2, well, they're classified by H2, S2, Z, which is isomorphic to Z, while the H3 of P, well, if this is a oriented case, then it's also classified by Z. It turns out that these formulas just interchange these two integers. So for instance, if I look at, say, the trivial case with 1 unit of h flux, so I take this to be 0 and this to be 1, then the dual is going to be something which has 1 unit of curvature, which is the S3, which is the Hopf bundle, and the dual will have 0 flux. So the claim is that string theory on these two spaces with these backgrounds are indistinguishable. So string theory actually doesn't distinguish the topology of the manifold. You can have equivalent string theories, but which live on manifolds which are topologically distinct. And that's sort of amazing. So maybe just with a philosophical remark, I finish for today. So if you want to, I guess if you want to, I guess the goal is to build a string theory which is manifestly invariant on the T-duality, but then you see here that the manifold itself is not a good degree of freedom to describe that theory with, because different manifolds can produce the same theory. So you need to think of ways of encoding the degrees of freedom of such a theory differently in such a way that the symmetry is manifest. Okay, we'll continue tomorrow afternoon.